Hi friends, in the last video we have learnt about ferromagnetism, right? For ferromagnetic materials, the relation between magnetic field and current is not simple. It is given by this graph or this loop, which you can call as hysteresis loop. And I have said that this gives the relation between magnetic field and current, but here you see B versus H, right? I'll tell you why. The magnetic field for current carrying solenoid is given by mu naught and I, right? Wherein is the number of turns per unit length. Okay. Then B is given by what? B is mu naught times H, right? This is equal to mu naught Ni. So what will I have? I got H is equal to Ni. Since N is a constant, as I increase the current, the magnetizing force or the magnetic intensity also increases. So even if I replace the H with current in this x-axis, the nature of this graph will be the same. So don't bother about it. Now this is the graph. Initially, I've placed a ferromagnetic material inside a solenoid. I'll start from here, from the origin, and let it be O. I slowly increase the current. I increase the H. Both are the same, right? Then this is my graph. From O, I go till A, this point A, in this way. It's not linear, observe that. This is called as a saturation point because I said you right, beyond a point, how much ever you increase the current, since all the magnetic dipoles are already aligned towards the magnetic field, no more magnetization can be increased. So this is the saturation point. Beyond that, you don't get any increase in the magnetic field. So it's meaningless to increase H also. That's why we'll stop here. And afterwards, what happens? I'll decrease the current. So when I decrease the current, the graph don't follow the reverse path. Instead, it follows this one. It goes from A to B. You observe that since it follows this path, even if I reduce the current to zero, I still have some magnetic field left. I mean to say that, first of all, the magnetic dipoles were randomly arranged. Since I applied some current, since I've got some magnetic field inside the solenoid, I've got these magnetic dipoles arranged in particular fashion. And when I reduce this current, because of the ferromagnetic property of that material, all of the dipoles are not randomized. There is still some net magnetization left over. I mean to say that there is still some magnetic field at B, even the current is zero. You got me? Even though the external magnetic field now is zero, there are still some dipoles which are pointing in this direction only, this previous direction only. That is the meaning of it. And this value of magnetic field when the current is zero is known as retentivity, or it's also known as remanence. And what I'll do after B, I will reverse the direction of current, and the dipoles were so strongly aligned to the previous magnetic field that even when I reverse the direction of current and go from B to C, still I have a positive magnetic field. I mean magnetic field in this direction. It means that even if I reverse the direction of current, still there are some magnetic dipoles pointing in this direction only. So till C, I have this scenario going on, and when I reach this C, my magnetic field becomes zero for some value of H, and that value of H is known as coercivity. You will understand the importance of these two terms probably by the end of this video. And what happens here, if I still increase the current in the opposite direction, then my path will be from C to D. Then the magnetic dipoles start getting aligned in the opposite direction in this way, and slowly as I reach the point D, all the magnetic dipoles are aligned in the opposite direction and no further alignment is possible. So this is my saturation point here, and the same scenario repeats from D to E. I go here, I reverse the direction of current, and again, not all the dipoles have changed their direction, even the current is zero. And from E to F, I'll go like this. And similarly, I have the curve from F to A again. So this graph uses two important quantities known as coercivity and retentivity. Here you observe that the behavior of ferromagnetic substance which you placed inside the solenoid depends on the history or the previous past. It appears that B is not exactly following H. I mean, even the current direction is reversed, and even after it is increased to a certain extent in the reverse direction, then magnetic field starts to change its direction. It appears that B is lagging behind, right? That's why you got this name, hysteresis. Hysteresis means lagging behind. Hope everything is clear till now. Let's move forward. Our next topic is permanent magnets. Permanent magnets are those substances which hold the ferromagnetic property for long period of time at room temperature. Note that they should hold their ferromagnetic properties. That's important. And how to prepare or how to make a permanent magnet. In olden days, I mean, before few centuries, what they were doing, say this is north, south, east, west. They were placing a bar magnet in this north-south direction, and they were just hammering it. Hammer it again and again and again and again. It finally turns into a permanent magnet. This was a this was the art followed by those people in olden days. In my childhood, what I was doing, I was taking a steel pin and I was taking a bar magnet and I was rubbing the end of this pin in the in same sense with one end of this bar magnet again and again, and finally it used to get some magnetic properties. It used to act like a magnet, but once you start playing with it, it slowly loses its magnetic properties. However, we now have efficient ways. The best way is take a solenoid, current carrying solenoid, and place a ferromagnetic material inside it. When you pass the current through the solenoid, the ferromagnetic material which you placed inside turns into a permanent magnet. And the key here to make a very good permanent magnet is to choose the right material as the core. For making a very good permanent magnet, you have to choose a material which has high retentivity and high coercivity. Of course, it should also have high magnetic permeability, that is mu. And why should it have high retentivity? Because once you switch off the current and take it out, then Br is what you are left with, right? That is that indicates the magnetic properties that are still left with it. I mean that indicates the strength of the magnet. So higher the retentivity, higher will be the Br and higher will be the or stronger will be the magnet. So you need to have higher retentivity to get a good permanent magnet. And if you have higher coercivity, it means that the magnet is not affected by external factors. It stays strong as a strong magnet for a long time. It is not affected by temperature fluctuations or physical body damage of the magnet, some things like that. A suitable material basing on these properties can be steel. That is very good. Other choices can be alnico, ticonal, and etc. etc. Now, we also have something called as electromagnets. Electromagnets are those substances which act as magnets taking the help of electricity. These electromagnets are used widely in many machines, almost in all the machines which have some moving components, say your CD player or electric bell, etc. etc. Now, the important thing about electromagnets is that they should act as magnets only when you want to. I mean, take this example. I want to create a circuit and I want to break a circuit actually. Say you have something here, some circuit, you have something, okay? Don't forget, don't bother about it. I want to break this circuit, okay? This is, uh, this is say made up of a paramagnetic material, At the beginning, it was in contact with this, okay? Now what I'll do, I'll try to place an electromagnetic here. It is done by placing a ferromagnetic material inside the solenoid. Here I have to pass the current, right? So what I'll do, I'll place a switch here. This is my source. So I want to break this circuit when I press the button here. So I'll push the button which has a metallic end so that the circuit completes here. Okay. Then what happens? Current passes. And when you have current passing here, this acts as a magnet. Since this part, this is made of some material, some paramagnetic material. This get at this gets attracted to this magnet in this way, and hence it bends. You observe this, and finally you have the circuit broken here. And when I take this switch out, when I switch off this button or switch something, I want the circuit to be reconstructed again, or I want this circuit to be joined again. So the key here is the electromagnet should act as a magnet only when current passes through it. Otherwise it shouldn't. That is the key. And when is it possible? It's possible if the retentivity is low. You got my point? If the retentivity was high, then what? It would have acted as a magnet even after switching off the current, and the circuit would never have been reconstructed again. That shouldn't happen, right? So here we want the retentivity to be very less, especially when you are working with electromagnets. Even this is done by right choice of material, and hysteresis curve helps you a lot to find the right material based on your purpose. And that's it. Our next chapter will be electromagnetic induction. Keep watching these videos. Thank you.